Hello, it's time to power up the inverter. Let's do it! Welcome back to EEforEveryone. In the last part of this series, we built this board. Now it's time to run it through its paces and see what it can do. We left off saying that we'll power this board up with 12 volts, and then use pulse width modulation and our microcontroller, controlling it from our digital interface, to produce a 16 volt peak-to-peak square wave. There's two things going on there. First, the 12 volts is being PWM chopped with a duty cycle to reduce the RMS voltage from 12 volts to 8 volts. And then the H bridge is then flipping that on its head, so we're getting plus 8 and minus 8, or 16 volts peak-to-peak, 50% duty cycle on that lower frequency signal, and then a higher 100 kilohertz frequency that is switching and being filtered out by our output filter. So we're going to power this up. If the board works correctly, and my math was correct, we should see very little 100 kilohertz noise on this output. And we should be able to achieve voltage regulation. My original plan was to use a 300 volt bus voltage for the final design, but as I thought about it more as I was soldering this together, I don't think we're going to need 300 volts. We might need one or 200 volts. 150 is still more volts than I'd like. 60 feels pretty safe. That gives me the warm fuzzies. Turn up to 80. I'd be a little cautious, so it wouldn't be too bad. I guess we'll see. I'll keep that in mind. I'll think about the voltage we need. Think about the use case. Let's see where this ends up. For now, let's work with what we have, with the power supply we've got on hand. Power this up off 12 volts. See how it runs. Let's go. While we clean off the bench and get things set up, there's something I need to tell you. You might notice that this video looks a little out of place when compared to our other recent uploads. To be honest, this video was recorded a long time ago. In fact, a very long time ago. Our mic was worse, our camera was worse, our lighting was worse. My plan was to re-record this footage and never let it see the light of day. However, some happenings after this was recorded both made that impossible and caused a debate over canceling this project as a whole. The setbacks that led to that point were numerous, involving time, money, and technical risk. Like we talked about in part 1 of this series, this circuit is no joke. It's dangerous. A UPS is a dangerous piece of equipment designed to be run unattended for many, many hours. This is a piece of equipment that handles enough power to be a fire hazard, electrocution hazard, and destroy thousands of dollars of connected equipment if something goes catastrophically wrong. I wasn't sure that I was in a position to do a careful and thoughtful enough job at designing this UPS to properly mitigate the risks at play in the system. I was not sure that my system architecture was set up in a way that made financial, safety, or technical sense. These thoughts were there for a reason, because they were true and I needed to listen to my gut. We'll talk more about this in the coming videos. What's more, recording videos in parallel with forward technical process is a very difficult thing to achieve. Believe it or not, creating electronics is a very different kind of work than creating videos, and switching between these two very different kinds of work quickly provides many challenges. I'd planned out a lot of different videos surrounding the bring-up testing of this board. We were going to have about 5 videos walking through the different layers of testing a prototype. This was going to highlight the many incremental steps of pushing the limits of a circuit further and further until we verified the full and complete functionality of the system. This incremental step process prevents blowing things up before you've learned anything from the board in case you find a defect. Why am I telling you all this? Well, because it isn't going to happen. Unfortunately, I got wrapped up in the excitement of testing our new board. We went through the STM32 dev kit you're about to see to a temporary Arduino solution and then ended up with the PSOC microcontroller that was actually able to meet our needs. I went through this process, but I didn't record it, and eventually we hit a point where the design failed. We hit a point where it failed one of our tests and it was made unrepairable. Building a new prototype wouldn't teach us anything new and cost another couple $100, and that just didn't make sense because of how much we'd already learned from the design through our testing. As we're going to discuss in a few days, I blew up the inverter, and because of that, I want to share what little footage was captured when testing the board, even if it isn't perfect. I hope you enjoy this slice of bring-up testing, the testing of our inverter prototype, and stick around for our next board, which will be the full UPS system. Next time, we will hopefully remember to keep the camera rolling for all of our testing, and not just some of it. So the inverter is on, 2.5 milliamps. This is going to be PWMing at low frequency. Now you see the current goes up to around 27 milliamps. Nothing's getting too hot. So it looks like all that noise is coming from enabling the A channel, which is where the PWM is happening. I'd believe that. And we can see on the output, there's a lot of ringing. Current waveforms aren't as interesting. The voltage waveforms, well, this is a much, much lower PWM frequency than it was designed for. So that would explain why it doesn't look quite right. But if we zoom out, oh yeah, that is disgusting. Alright. Got some updated firmware, cranked up the PWM frequency. Got some upgraded firmware. Should be trying to make a sine wave now. See how that goes. Oh, wow! Oh, it's working! It's making the sine wave. Holy cow. Oh, that's cool. Okay, math. $13.5. So if the scope were measuring accurately, we would be getting 19 volts peak to peak. Holy cow, so that bus voltage is coming through pretty perfectly. She gets pretty noisy when she's under load. Those resistors get pretty hot when she's under load. I like this. But I wonder how the story changes when we add bulk. Notice how the rail goes pretty nuts. I think it's time that we add our bulk capacitance to the story. Okay. Well, we've got the starts of a sine wave. There's definitely an issue with my logic shifting circuitry because the 5 volt input works great and the 3.3 volt input doesn't work. Clearly, as you can see from that scope capture, we've got a long way to go. Why? I can't hold on to it anymore. It's too hot. It got so hot on the lead that I couldn't touch the lead. Yeah, those are really hot resistors. Might need to rethink my method of loading if this is how it's gonna be, but hey, I'll try to get the proper control system up. At least try to get the more powerful microcontroller driving it. Right now, this is looking pretty promising. I hope you liked this video. That was a lot of fun. We got her powered up, tested her out, and it worked great. We didn't even have to do any modifications. The design worked well, and I'd like to give credit to the design review process. This board wasn't just looked at by myself.
I printed off all the design files, took a look at them with an objective point of view, and really tried to dive in and look for mistakes. I found a lot of little errors throughout the design and I fixed them. I then gave these to a friend, and my friend took a look at all the design files and found a few more issues, which I then corrected. All of that together couldn't have left this board in too bad a shape. Between the two of us, and obviously a pretty careful design to begin with, I think we'll be in good shape. So let's crank this board up in the next video. Let's go from square waves to triangle and sine waves. And let's see if we can close the control loop instead of driving this open loop. That's in store in the next one. If you think that this inverter project is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!